Welcome back to geometry. So we are jumping into probability now, and we're talking about the experimental and theoretical probability. So the notation is going to be a little bit different. So we have this here, probability of A is the probability that an event A will occur. Or we occasionally might write it this way, the probability of A is the number of ways not X, but A can occur. And much of what we do in probability is figure out how to count that. We're going to just scratch the surface of this in this class. But there's a lot to that. And the denominator is the number of possible outcomes. So in this class, we're going to cover some basic scenarios like what's the probability of reaching in your drawer and pulling out a yellow sock? Well, let's say you have 2 yellow socks out of 20. Well, it'd be 2 out of 20, which reduced to 1/10. So that is our basic definition of probability. Well, this section's called experimental and theoretical probability. So let's talk a little bit about the difference between those. So what we're going to call experimental probability would be, let's say that you go up to 100 people, you ask 100 people how much sleep they got last night, about their sleep, we'll say. And let's say that 64 responded that they got more than 7 hours of sleep. It's pretty good. So of course 36 got less than or equal to 7 hours. So if you want to know what is the probability that one of these people, let's call X, probability that X is greater than 8 hours sleep. Let me redo that. That would be 64 out of 100. That would be an experimental probability. And we're not going to do a whole lot of that because we're not going to be doing experimentation. This would reduce down to 16 over 25. You always want to reduce your fractions, or you could write it as 64%, or you could even just say 0.64. So I guess I should have done this probably. That's good. So that becomes 0.64, or you could write that as a percentage that way. On the other hand, theoretical probability, which we'll do a bit more of here, you're dealing with a scenario where you know what the probabilities are. For example, find the probability of rolling doubles with 2 dice. I think our book calls them number cubes. So this is the way you write that, probability of doubles. What is it? This is a fun problem. Dice provide a great deal of good problems. Well, here's our possibilities. We can get a 1 and a 1. We get a 1 and a 2. We get a 1 and a 3. We get a 1 and a 4. We get a 1 and a 5. We get a 1 and a 6. But we could also get a 2 and a 1 and a 2 and a 2 and a 2 and a 3 and on and on and on. A 3 and a 1 and on and on and on and on and on. Right? So this would come down to 2, 6. This would come down to 3, 6. This would come down to 4, 6, 5, 6, 6, 6. This would be 6, 1, and so on. So you're going to have 6 this way, 6 options this way. We know that means there's 36 total scenarios. Now, how many of those are doubles? Well, there's 1. There's 1. 3, 3 would be here. Would be 1. 4, 4 would be here. About 5, 5 would be there. 6, 6. There's 1, 2, 3, 4, 5, 6. 6 out of 36. which reduces to 1/6. And there we go. That is a theoretical probability. If you are playing a game with 2 dice, which is pretty common, like Monopoly, you should get doubles about 1/6 of the time, which is interesting because that's how often you get any given number on a single die. So if you roll a single die, what's the probability of getting a 4? It's 1 in 6. Probability when you roll 2 dice of getting doubles is the same, 1 in 6. There are a number of games out there that knowing these probabilities can be useful if you play Settlers of Catan. That can come in handy. A few others out there as well. Okay, by the way, this thing I drew here, I didn't draw them all. It's getting kind of tedious. But we often call this the sample space. Those are all the possible outcomes. This is actually in your book on page 826. They give you that entire sample space, and you can see that organized there. Let's look on page, I know you can't see this, but page 825, got it number 1. It says, a park has, let's kind of take notes as I go through this. A park has 538 trees. You choose 40 at random and determine that 25 are maple. So you're going to choose 40 at random. That's called a random sampling. And we got 25 maple. Let's say 25. I thought they were going to give us another one too. So 25 are maple. Let's do that. So 25 are maple. And it says, what is the experimental probability that a tree chosen at random is a maple tree? Okay, so that means 25 of your 40 were maple. So we could say the probability of maple is 25 over 40, which reduces to 5/8, or 0.625. That's if you put in your calculator. Or move the decimal over 2 and put a percent, 62.5%. Any of those 3 is fine for an answer. So that's the first question they asked. That's the experimental probability. It's experimental because you actually conducted this experiment. You went out and selected 40 trees randomly. You wouldn't want to select them all together. You might find an aspen grove of trees or something. They're probably more likely to be clustered together. You want to pick them in random locations throughout the park. Then it says how many trees in the park are likely to be maple trees. Well, based on this, I know that I can multiply this experimental probability by the number of trees, right? So every tree, there is a 0.625 chance of it being maple. So I multiply that by 538, and I'll expect it to be a little bit over half. And I did not write the answer down. Actually, there it is, 336. So we'll get about 336 are maple. And I think that is an approximation. I think it was 0.5, but we rounded to the nearest whole number. So 336 maple trees in the park, which is indeed greater than half. Got it number 2 is on page 826. I want to take a look at that one too. It says, back to the dice problems, what's the probability of rolling a 9? Okay, so rolling 2 dice. Now, of course, this is a sum. There is no 9 on the dice, so probability of rolling a 9. If I'm going to go back up here and look at my options here, see if I find any that add to 9. None of the first column do, none of this column do, but there's a 9. Another 9 would be 4 and 5. Another 9 would be 5 and 4. Another 9 would be 6 and 3. So there are 4 chances to get a 9 out of, we already said it was 36. It's the same thing as 1/9. So a 9th is only a 1/9 chance. Where, look at that, a 2 only 1 in 36, or 12, only 1 in 36. There's only one way to do it. The most common is 7. You see there, let's use a new color here. 1 and 6 gets 7, 2 and 5 gets 7, 3 and 4 gets 7, 4 and 3 gets 7, 5 and 2, and also 6 and 1. The next one, same instructions, but they say the probability of rolling a 2. Well, I mentioned that a second ago. There's only one way to get a 2. It's a 1 and a 1 out of 36. And finally, the probability of getting a 13. Let's look. The biggest would be 6 and 6. That's only 12. There's no way to get 13. This is 0 out of 36. 0% chance of rolling a 13. So don't count on that. A couple of other quick things, and we will wrap this section up. I need to talk about the idea of a complement of an event. Complement. You know, we talked about complementary angles. This is not the same. So if you have a complement of an event, it's like saying if the probability, let's just do this example. Probability of rain, let's say a weatherman says 40%. Right? Then the probability of it not raining would be 60%. Because it's going to rain, or it's not going to rain. Say you apply for a job. The probability you get the job, let's say, is 4%. Not 4%. We'll say 61%, or 0.61, right? Well, then the probability of not getting the job would be 39%, or 0.39, because you'll do one or the other. You get it or you don't. You get into that college or you don't get into the college. Or I guess there's waiting lists and all that kind of stuff too. But that will say that's not. You're either in or you're out. So this idea of complement is here. The probability of not an event happening is 1 minus the probability of the event happening. So that's how I got 0.6, because I did 1 minus 0.4. That's how I got 0.39. I did 1 minus 0.61. So that is, it can be really powerful. Sometimes it's difficult to find the probability an event's going to happen, but or it's often easier. Sorry, sometimes it's hard to find the probability of an event not happening. Sometimes it's easier to find out it does happen and subtract that from 1. There's some great examples of that. We're just not really ready to get into that just yet. So let's say this example. Let's say you have 4 black socks. You have 6 white socks. And 2 brown socks. Oh, those are your favorites, I'm pretty sure. What is the probability that you reach in, you grab 1 sock? What's the probability that it's not a black sock? Well, you could do the probability that you get a white plus the probability you get a brown, right? That would work. But I could also do it this way. It's 1 minus the probability of getting a black. So 1 minus probably getting a black. There's 4 black socks out of 12 socks, which is a third. 1 minus a third is 2/3. And yes, you could have done this. You could have done the probability of white socks plus the probability of brown socks, which would be 6/12 plus 2/12 equals 8/12, or 2/3. It works. But what if there were 20 different sock colors? rather than adding up all 19, you could just do 1 minus the probability of the black socks. Much faster. Let's do another dice problem. Let's say you're rolling 2 dice again. Rolling 2 dice. And I want to find the probability, the sum of dice is greater than 3. So that would mean 4 is okay, 5 is okay, 6 is okay, 7, 8, 9, 10, 11, or 12. Do you really want to add all of those up? 9 numbers? That probability plus that, plus that, plus that, plus that, plus that, plus that, plus that. No, I don't want to do that. Instead, I can do this. It's equal to 1 minus the probability that the sum is less than or equal to 3. So I can do 1 minus the probability of 2 plus the probability of 3. Well, less than 3 or equal to 3 would be, as I said, the probability of getting 2 or the probability of getting 3. Look back up at the table. There are only, not use the color here. That is less than or equal to 3. That is, and that is. That's it. No. So there's only 3 out of 36 ways to get a number less than or equal to 3, which is 1/12. So the answer here is actually 11/12. So if you're playing a game and you need something bigger than 3, anything but 3 or 2, you have an 11 and 12 probability. So it's looking pretty good for that case. I did want to wrap things up. And how are we doing on time here? Just under 17 minutes, with just a couple of quick examples. I'm going to follow along with in the book on page 827. I like to do 1 through 3 and 6. Number 1 says you're going to spin this spinner. What's the probability it lands on an even number? Well, it goes 1, 2, 3, 4, 5, 6, 7, 8. Well, that's nice. So there's 4 evens out of 8 total outcomes. So that's 1/2. Number 2, it says a number greater than 5. Well, that would include 6, 7, and 8, so 3 8s. Number 3, a prime number. Ooh. To review our prime numbers, 1 is not prime, 2 is prime. So it's a number divisible by itself, only divisible by itself and 1, but they have to be unique. It can't be 1. So 2 is prime, 3 is prime, 5 is prime, 7 is prime, 11 is prime, and on and on. So the only ones on that list would be these 4, so that's 4 8s or 1/2 also. Also looking at number 6, it says your friend says the probability of rolling a number less than 7 on a standard number cube is 100. Explain your friend's error and find the correct probability. So you don't say the probability is 100. You say the probability is 1. I don't remember when this comes up, but so the probability of a certain event is 1, not 100. And the probability of an impossible event is what? Is 0. So this one, they were wanting that probability of a certain event is 1. Well, that is 13.1. That is the longest section. 13.2 and 3 are very